Okay, differentials. Recall that dy over dx, the derivative, is equal to f prime of x. Well, if we take this and we multiply it out, we get this here. It says dy is equal to f prime of x times dx. Now the dx and the dy, when we pull them off by themselves, those are called differentials. And differentials can be thought of as approximate small changes in x and y respectively. That's supposed to say in x and y respectively. So what I want to do is look at sort of an example to get started on this. So suppose you have a metal square and it initially has dimensions of 3 by 3 inches. And then the metal square is heated up and it expands to 3.08 by 3.08. I want to do two things here. I want to find the exact change in its area. And then I also want to use differentials to approximate the change in the area. All right, so let's see, we've got 3.08, or rather we're going to start with a square that's 3 by 3. So the area of this thing is 9. And then when it grows to 3.08, the area of this is going to be, let's see, 3.08 squared is 9.4864. Okay, so it increases in area by 0.4864 square inches. And so that's the exact change is 0.4864. And that's easy enough to do on this with this function. But with other functions, it can get a little messy. So let's look at how to do this with differentials. So we need a function. The function we have here is area is x squared. Now if I take the derivative of a with respect to x, I get dA dx is 2x. And if I multiply both sides by dx, I get dA is 2x dx. Now, here's sort of where that comes in. If we take this square that's 3.08, I'm going to draw in two things here. Okay, this is my original 3 by 3 square here. And it increased its area by adding on this bit up here and this bit over here. If you look at those two parts, the areas of those two things, this rectangle over here, well, let's see, this rectangle here, its area is, if we call this right here a change in, I'm going to call this dx, and I'm going to call this up here dx. So it's like dx is the change in the length. So if we add up this square here and this, rectangle, and this rectangle here, if you look at it, the area of one of these rectangles is 3 times dx. So if I come down here and I look at this, dA is going to be 2 times 3 times 0.08. All right, so that's 6 times 0.08 is 0.48. That's approximately the same as this up here. Now, of course, what's it leaving out? It's leaving out the little square up here in the corner. This little bit up here winds up getting ignored. And that's why this is only an approximation instead of the exact amount. But we can use differentials to approximate the change in area. So that's what this says down here. Given a function, y equals f of x, and a value dx representing a small change in x, the actual change is approximately dy, which is f prime of x times dx. And you can also word this in terms of error. Like if you're given some function and a value of x representing an approximate error in x, and you'd also be given in both of these you would be given a particular value of x. I should add that. Both of these, the error, well in this case the error would be approximately this. And up here the change in y would be approximately this. So I want to do some examples, but I'll save those for the next video.